to field performance on appropriately conditioned specimens. So this balanced mix design addresses multiple modes of asphalt layer distresses, considering the mixture aging, the traffic conditions, climatic conditions, and the pavement location where it's being placed. So the key takeaway from this definition of this balanced mix design is that this balanced mix design is a design philosophy that's used to optimize mix performance against distresses pertaining to the region where it's being placed and the traffic and the climatic region where it's going to experience. So unlike these traditional methods, balanced mix design combines along with this volumetric testing that has been used traditionally to have a comprehensive design approach in terms of resiliency and durability aspects. So this is one way how balanced mix design addresses the performance gap. So one of the significant reasons for adopting balanced mix design by state agencies is the limitation with the current volumetric mix design. So I mentioned before, there are some limitations with this our existing volumetric mix design system, especially with now dealing with new materials that you are seeing over here with all the figures that you're seeing over here. So with the traditional volumetric design, we face a major challenge, and that is we don't have a reliable way to predict how these different new materials will affect performance. So for example, you see on the top left corner, you have RAS material that's being added, and fractionated wrap is another one of the new materials, and other materials as well, like plastics, fibers, and additives. So just to give like a reason why, so RAS, when you're adding into the mix, it can stiffen your mix, but most of you may be familiar, like it may lead to embrittlement or brittleness of the asphalt mixture over a period of time. And fractionated wrap, when you're dealing with fractionated wrap, the quality of these wraps would vary widely. Especially now we are using first generation wrap, second generation wrap, and third generation wrap. So if you're using this wrap over and over, the quality of this mix is going to change significantly. Although you would meet the volumetric criteria, the overall performance is being impacted when you're using fractionated wrap. And as far as like plastics and fibers, these properties are known to enhance certain properties of the asphalt mixtures, but they're not the performance of this the materials are not completely understood. So it's necessary to evaluate the performance of this new materials that are being added into that asphalt mixtures. And with additives, most of you also know, like it's being used to improve workability and durability, but it still needs proper evaluation of how this new materials are impacting the performance. So that's one of the reasons why we are saying like balanced mix design is something we need to focus now. With this balanced mix design, we can handle the implementation of new materials that are available in the market to extend the life and durability of this asphalt pavements. So just to give a brief overview, like what are the current methods that are current methods of mix design that are being used right now. So typically you use for look for your aggregate gradation, that is see if all your aggregates are distributed within the tolerances, and then they're meeting the specific design tolerances. And the second one would be like your asphalt content as well, like whether it's designed to optimum binder content with target values, with target binder content, and with their appropriate production tolerances as well. And the third way that you look at this design is evaluate is through this asphalt mixture volumetrics, specifically voids in mineral aggregates, air voids, and voids filled with asphalt. And most state agencies use minimum VMA criteria to see if they're meeting that expectations of their performance, of the mix performance. And in the field, when you're looking at that field, you have density specifications as well, and you need to have that density requirement as well. And then you have this asphalt binder testing to evaluate whether your PG binder is meeting the expected performance and are having the appropriate viscosity grades. Then you evaluate this riding quality measurements using you evaluate this riding quality measurements, and then you also make adjustment using inertial profilers. Then you have this contract testing with agency verification, and then you have the statistical acceptance as per IRC codes. So this graph that you're seeing over here, you can have a look at the motivation for this BMD, why we are now talking about this balanced mix design. So this is a trend over the 40 years. So it's basically like with this, it's almost the time when the NATPAC was initially established. So since 1980 all the way to 2020, it's a 40-year trend, and you could see on the vertical axis, it's a cost of a PG6722 binder per ton recorded in the state of Mississippi. Like the data is coming from the state of Mississippi, and the y-axis you'd see the 40-year period. So what you see over here is the average price for a PG67 binder from 1980 to 2005. 1980 to 2005 was $138 per ton, and this was during this Marshall era. At the top, you would see like all the different eras: the Marshall era, the Super Pave era, as well as now the balanced mix design era that we are right now in. So yeah, as I mentioned, like in the Marshall era from 1980 to 2005, the average price of binder of a PG6722 binder was $138 per ton. However, after the Super Pave implementation began, the price significantly increased. So you would see like from 2006 to 2020, the average cost of this binder was $459 per ton. And this is for PG6722 binder. However, if you're using like a stiffer binder, like a PG7622 grade, you would see that the price bump to be like $598 per ton. And over years, like you would see at the top, there's been an increasing trend in the use of recycled materials and volumes. So materials like ground tie rubber was introduced in like 1990s, and then the introduction of RAP in the early 2000s, and then RAS in the late 2000s. Now recycled engine oil bottoms, and now plastics as well. So over the years, there's an increasing trend of using recycled materials and volumes. So the traditional Super Pave system that I've been using over here was designed for a different environment. So what you're seeing here is like the Marshall era, the market was completely different in regards to like the binder cost and everything. And with Super Pave, the market was different. Now with this inclusion of this recycled materials, the market is completely different. Hence, there's a need to evaluate the performance of these recycled materials that are being introduced into that asphalt mixtures. So BMD is one way that integrates this performance testing into volumetric design, ensuring the mixtures can handle diverse modern materials while maintaining durability and resiliency performance characteristics. So this is one neat overlook of this 40-year trend, and this would significantly change moving forward as well. So over the years, we have to adapt ourselves to new technologies, new methodologies of mix design. So one significant development in the asphalt industry is the advent and popularization of mechanical test for asphalt mixtures. So this change has been crucial for us to improve our understanding of these new materials and prediction of this mixed performance of these new materials. So the mechanical tests provide a way to more accurately assess the mixture under different climatic and traffic conditions. This test, this test most commonly focus on two distresses, mainly cracking and rutting, which are critical for pavement durability. So the figures that you're seeing here are all the typical cracking and rutting tests that are being used for, that are being considered for BMD implementation. So the one on the left that you're seeing over here is the ideal CT test, or the indirect tension cracking test. And this one, you're fabricating a gyratory specimen, and you're basically cracking in half and evaluating this cracking potential of that asphalt mixture. And the next cracking test that is considered for BMD implementation is this Illinois flexibility test, the middle figure that you're seeing over here. So this Illinois flexibility index test it's more fracture mechanics oriented. Unlike this ideal CT, which is a very simple and practical way, the Illinois flexibility test is more engineered involved, like fracture mechanics involved, where you have to slice the surface of this asphalt specimens, and then you initiate a crack and then see the overall flexibility and the stiffness of the asphalt mixtures. And then the bottom middle picture that you're seeing over here is the Texas overlay tests that are considered by some states like New Jersey and TxDOT. And what this test does is, like, it simulates reflective cracking. So if there's an asphalt overlay on top of concrete, how many number of cycles does it take for that asphalt specimen to crack into two halves? So based on the amount of cycles, you could estimate the fatigue life of these asphalt mixtures. And the last two rutting tests that I'm going to talk about, this ideal rutting test, or the rapid shear rutting test, and the Hamburg wheel tracking test, which most of you are familiar. So the rapid rutting shear test was developed in terms of production capabilities. Like, so during an actual production, is it easy to fabricate and evaluate quickly the rutting potential of this asphalt mixture? So that's one of the reasons why they developed this rapid rutting shear test, and that is one of the tests that is being considered by many state agencies. And the Hamburg wheel tracking test, it's as you know, like, it has a steel wheel rollers that passes back and forth, and that measures the stripping potential as well as the rutting potential of these asphalt mixtures. So all these tests are basically evaluating the performance that's supposed to simulate the field conditions. So this allows us to better predict how these mixtures will behave under different traffic and environment conditions. So now let's discuss what this balanced mix design approach is talking about, or what it entails. So the BMD approach focuses on balancing two key properties that you're seeing over here on the graph. Like one is the cracking resistance, the other one is the rutting resistance. So on the graph, the vertical axis represents the cracking resistance, and the horizontal axis represents the rutting resistance. So the goal here is to ensure that the mixture, so for each of these cracking and rutting tests, you have a set criteria based on your past experience. You would develop a set criteria, like you have each of these mixtures should meet a minimum requirement of this cracking and rutting performance. So it's like a pendulum. So you have to balance between both cracking as well as the rutting aspect. So the goal here is to ensure that the mixture, say for example, if it's passing the cracking resistance but is failing in rutting, but you need to bring it to that the criteria of both cracking and rutting to maintain an optimum balance. So this balance you could ensure by changing your asphalt content, gradation, and the binder type to achieve this desired balance. And that's what this balanced mix design approach is, like, where you're adjusting your volumetrics to achieve the desired cracking and rutting performance. And so for example, like if you take a mixture, each of these mixtures would meet the volumetric criteria, but may not perform equally. So in order to ensure that both of these mixtures performs better, you may need to adjust your asphalt content, effective asphalt content, for example, or your gradation as well to enhance that performance characteristics. So BMD allows a way to work around your volumetrics to achieve this cracking and rutting performance. So the current practice recognize that achieving a fully balanced mixture may not always be feasible. So this is well known that you cannot have a completely balanced mix that meets both cracking and rutting criteria all the time. So DOTs use various strategies to achieve this performance, acknowledging that some flexibility is needed. So the ASHTO PP 105, if you read it, it mentions that there are like 4 approaches or 4 alternatives to this BMD implementation process. So in approach A, there's full compliance with both volumetrics and performance requirements. So this is most a conservative approach, offering low flexibility and innovative potential. So you can't innovate more. You're fixed on the volumetric design with some performance verification. In approach B, you would require full compliance at the preliminary optimum binder content, OBC, or the optimum binder content. And the performance is optimized through moderate changes in binder content, like what I mentioned before, like you would change your binder content and then optimize it. So this approach is slightly more flexible than approach A, but it still lacks innovative potential. And approach C allows some volumetric requirements to be relaxed or eliminated. So it's kind of a balance between both the volumetric and the mixed design testing. So here the performance is optimized by adjusting the initial binder content or the mixture component properties. And this approach is less conservative and offers a medium degree of flexibility and innovation. And finally, the approach D has limited or no volumetric requirements at all, like completely void of volumetric approach. And the performance is optimized by adjusting mixture components and proportions. So this is least conservative approach, providing the highest degree of flexibility and innovation. So if you want to look at the low risk category, that would be like approach A and B, and even C, whereas D is a more risk involved approach. And based on our survey, like 2 of the states are currently using the approach D, like Alabama and Tennessee, I guess. The 2 states that are predominantly looking into this approach D. So let's explore like some of the options for acceptance with BMD, or potential options for acceptance with BMD. So the first option is to maintain the status quo, like where BMD is applied at design while continuing to use the traditional acceptance quality controls during production. So the second option is verifying, the second option involves verifying BMD on initial production lot and then reverting back to the traditional acceptance quality controls. So this ensures the initial compliance with this balanced mix design testing before regular production quality controls that you typically perform. And the third option combines both the balanced mix design for acceptance with some traditional acceptance quality controls. So this hybrid approach leverages the strength of both the methods. And the final option is the exclusive use of BMD test alone, not even worrying about the volumetrics, just BMD test for acceptance. So this, as I mentioned, is a high risk category, and you have to meet the performance criteria established by that BMD without relying on this traditional acceptance quality control. So the key takeaway from this method or the options is that BMD is not a one-size-fits-all approach. So based on your project needs, different projects, different mixes may require different acceptance strategies based on specific needs and conditions. So these options provide flexibility for agencies to adopt BMD in a manner that best suits their operational needs. So one of the other advantages of using this BMD is BMD has the potential to significantly contribute towards sustainability in payment design and maintenance. So one key aspect is by using this BMD in mix design, you're contributing to the overall life cycle analysis. So what I mean by that is like this method evaluates the environmental impacts of a product or process over its entire life cycle, from raw material extraction to the end of its life disposal to the design life. So BMD helps to optimize materials and processes to minimize the environmental impact. The other aspect of this BMD implementation is this life cycle cost analysis, so LCCA. So this approach assesses the total cost of the ownership over the life of an asset. So this ensures that the payments are designed to be more durable and require less maintenance, which can lead to significant cost savings over a period of time. So incorporating balanced mix design into practice not only enhances performance, but also aligns with sustainability and resiliency goals, making it a comprehensive approach to modern infrastructure development. So there's I just posted a Federal Highway link that talks more into details about sustainability and the balanced mix design, performance-based mix design. So now let's discuss why we need to change and why we need the change and what are some of the benefits of this balanced mix design. So many experts over here would, on this presentation, would acknowledge that all the mixes behave completely different. So current design procedures may not be optimized, may not meet the expected performance using volumetrics alone. So we all feel that the volumetrics is not able to answer all of our questions regarding the performance. So this means that, for example, the two mixes with similar volumetric properties can still perform completely different in an actual field conditions. So that's something that many of us have experienced over the years. So by implementing balanced mix design, we can address these differences and achieve several key benefits for Asphalt community. So first, like the balanced mix design can enhance quality and longevity of payments. So by using performance tests, we can ensure that mixes are durable and fit for their specific applications and decide climatic conditions and traffic conditions. Second, BMD creates a stronger connection between the design elements and the actual field performance. So this means like we can predict how a mix would perform more or less accurately by using this performance, mechanical performance tests. And thirdly, balanced mix design supports the use of more alternate and recycled material. As I was showing on the graph, like over the years, the recycled materials that are being introduced in the mix have been increased in the context of sustainability and resiliency. So this is something that's crucial for sustainability aspect and also the cost effectiveness in modern pavement construction. And we are also are in dire need of an alternative to conserve our virgin aggregates and binder. And finally, like the BMD encourages industry innovation to meet performance needs. So it allows more flexibility for the contractors and give them flexibility and creative in mix design, leading for better performance payments. So in summary, like BMD can lead to better performance, more durable and more sustainable payments, addressing the limitation of this volumetric mix design approach. So like just to summarize whatever I've been covering up to now. So BMD, as I mentioned before, incorporates mechanical performance tests to evaluate asphalt mixtures resistance to multiple modes of distresses like cracking and rutting, and evaluate their performance in real world condition. So by addressing specific regional traffic and climatic condition, BMD optimizes asphalt mixture for enhanced durability and performance conditions. So this tailored approach ensures that mixtures are suited for their specific environments. And BMD effectively accommodates the increased use of recycled materials such as RAP, RAS, plastics, fibers, etc. So this ensures that mixtures remain durable and cost-effective while promoting sustainability. And BMD combines volumetric properties with performance criteria, providing a comprehensive framework for designing high-performance asphalt mixture. So this holistic approach ensures that all aspects of mixtures are considered and optimized for maximum performance. So in summary, BMD offers a robust, adaptable approach to asphalt mixture design, addressing modern challenges, the current challenges that we are having, with a focus on durability, sustainability, and performance. So now we know that what is balanced mix design and the theory behind the balanced mix design. Now I'm going to talk about linking theory to practice, and I'm going to showcase the case examples of Vermont DOT's experience with this balanced mix design implementation. So now you might be wondering, like, why should I care about their case example? It's a completely different state, different country. Why should I care? And what are you getting out of this presentation? So what we'd like you to understand is, like, we would like to showcase this as an example, as a research, like this case example serves as a good benchmarking for an agency. So this research effort would help other agencies how their approach is towards balanced mix design. And through this balanced mix design benchmarking, use that information to analyze mix design properties versus balanced mix design index properties. So how your typical volumetric is and how the balanced mix design is comparing, how is it relating to each other. So that we can understand based on this case example. And what makes this work unique is that this research work that we were performing were looking at the analysis of production variability from the data provided by VTrans. So like how this production variability would impact your overall BMD parameters in a statistical acceptance program. So with production variability, you may have, like, your asphalt contents would change, your gradation may change, your performance of this the quality of your wrap would change. So how all this variability is impacting your overall BMD test results. So this is where, like, the data from this VTrans would help in assessing that information. So right now, like, so one of the reasons why VTrans was moving towards balanced mix design is, like, the VTrans law has mandated, like, the use of up to 50%. Sorry. Yeah, Vermont state law had mandated up to like 50% RAP by aggregate weight since 2008. And the problem with, like, even though the state law allows this 50% RAP to be used in that asphalt mix, we know that like the state law is looking into the aspect of sustainability and conserving the natural resources. But even though you allow 50% RAP, the maximum allowed RAP by the VTrans agency was 20%. The reason being like that's Vermont is a cold state. And when you're adding like more than 20% RAP in your mix, you're basically making the mix stiffer. And when you make the mix stiffer, you need to grade bump your binder grade as well. So this would impact the overall performance of your mixes. So Vermont was sticking just with a maximum allowable RAP percentages of 20%. Though the state allows up to 50%, they were limited to use only 20% RAP because of the grade bumping of the binder that's being used. And the other one was like the 3% RAS by aggregate weight was added into the specification, Vermont specification. And as I mentioned before, like in the state law amended in 2022, like under annual transportation budget, sustainability was a major factor that they wanted to bring into building components. And some of the distresses that Vermont agencies was experiencing by including this recycled materials was rutting and graveling. These were the one of the major issues that they had in Vermont. And when I'm talking about the cracking, they had all sorts of cracking issues, primarily like fatigue cracking, thermal and reflective cracking. And with the original SuperPave performance test that they had implemented, they couldn't include this performance test because it was too complex for Vermont agency in terms of training a technician and understanding how this performance would impact the performance test results would impact the overall performance of that asphalt mixtures. So since it was too complex, the performance testing was too complex, they just stuck with the traditional volumetrics part of that SuperPave performance testing. So right now, most of the state agencies over here have successfully implemented the original SuperPave requirements. That is the asphalt binder specification, the volumetric design, and the mixed performance, not the mixed performance, just the asphalt binder specification and the volumetric mixed design procedures to help address rutting. Most of you may or may not be familiar, but back in the days in the 90s, rutting was a major issue. And with the SuperPave, introduction of SuperPave, they had resolved the issues with rutting. But now with the introduction of recycled materials and everything, they started having issues with cracking now. So this cracking and rutting issues was a major reason why the performance analysis was required. The mixed performance analysis was required. And the reason why it was not being adopted was because it was too complex for their to understand by the state DOT personnel to assess the mixed performance. And as asphalt mixture design following the SuperPave volumetric design became more stiffer, like as I mentioned, with SuperPave, the mixes became more stiffer and stiffer. And the state agencies were increasingly concerned about this mixture's ability for cracking and durability. In terms of cracking and in terms of cracking and durability, especially the growing concern in the increased use of RAP and RAS. So they felt that there is a need to develop an asphalt mix design procedure considering performance tests to address multiple modes of distresses. So that was a major concern by the state agencies. So the table over here shows the overall VMD implementation that's currently happening now as we speak. So these are some of the 10 or 7 states VMD implementation progress. And as you can see, different state agencies have a different need on why they're using the balanced mix design method and the different cracking tests that they believe are more representative of their actual field performance and the respective rutting tests which simulates field condition. And you see that all the states are in a different status of BMD implementation. So what sticks out from this table is like each of the states use different mechanical test, and which of this cracking tests is more representative of field performance, and how do you harmonize these different performance test results? So the test protocols that are used for all of these tests may vary as well from state to state. So that's something with balanced mixed design implementation, you need to see which of these tests is more replicative of the field conditions. And since this is a case study on Vermont, I'm going to talk about the rationale behind why Vermont chose this two test for BMD. So back, one of the tests that the Vermont agencies was using was the Hamburg wheel tracking test. And the reason why they were using Hamburg wheel tracking test is they had a lot of issues with raveling. As I mentioned before, they had issues with raveling, and they suspected it to be moisture susceptible related. And plus, the neighboring state like Maine also had this experience with moisture susceptibility. And Maine had a success with the Hamburg wheel tracking test that enforced Vermont as well. Like, hey, Maine is having a good success with Hamburg wheel tracking test, and let us try adopting the Hamburg wheel tracking test to see if it's simulating field conditions. And the other issue with the traditional approach was that they were not confident in the Astro T283 standard or TSR method because of the Vermont's climatic condition. It didn't properly simulate the exact field conditions, and they failed. And that's one of the reasons why they moved towards Hamburg wheel tracking test. So Vermont actually purchased this device in 2015 and began evaluating the Hamburg wheel tracking test in 2016. And this is for the rutting aspect. And for the cracking aspect, they started with the Illinois flexibility test. And the reason why they chose was this was one of the tests highlighted to look at the thermal and fatigue cracking as per the NCHRP report 9-57. So this Illinois flexibility test was used to address some of the issues that they had with using 20% RAP. And this Vermont started actually purchased this device in 2017 and began evaluating in 2018. And what they felt was like with this Illinois flexibility index test, they found that it was not practical because right from the sample fabrication of this Illinois flexibility test to the final test result that you're getting, it was about like 3 days, because like you're fabricating a specimen and then you need to slice the ends of the specimen, create a notch, bulk them, and then you have to test them. So it's time intensive method, process for Vermont. So they started looking into the another test or like a surrogate test to supplement this Illinois flexibility test. And that was the indirect tension cracking test. And this was also like they recently purchased in 2019 and began evaluating in 2020. So they found a good success with this Illinois flexibility test, and they wanted to use the ideal CT because of its simplicity and cost-effective nature of that test. They started using ideal CT as a surrogate test. So for this study, V-Trans conducted several performance on their plant-produced asphalt mixtures. So all the performance testing that was done on plant-produced acceptance samples collected by V-Trans. Yeah. So these samples, what they did was they put a sample, they reheated to fabricate the specimens for volumetrics and BMD testing without any additional laboratory aging. So they never went to the extent of aging to simulate field condition over 10 years, but like they just reheated the mix, fabricated the specimens, mechanical test specimens, and conduct some testing. So, and the data that they collected were from the last 4 to 5 years since 2018. And VTANS was originally looking at Hamburg wheel tracking and iFit since 2018 and added Ideal City since 2020. So the graph over here shows the overall steps that are needed for the BMD implementation. So let me see. Yeah, so the graph over here shows the overall BMD implementation process. And the overall BMD implementation process involves like 8 different tasks. And this balanced mix design is not like something that you do it immediately. It takes about 8 years. So from to successfully implement balanced mix design. So the first year you would see from this Gantt chart is like the initial, each of these tasks would take somewhere between like a year to almost like 5 to 6 years. And by the time you go to that overall implementation, it's probably about like 7 to 8 years. So this Gantt chart provides the overall implementation process. And not all process may be considered for this balanced mix design. So with this case study, the task we were assigned was to establish the baseline data. So what this baseline data is like reviewing historical data and information management system, conducting benchmark studies, and also conduct shadows projects just to see the overall performance, analyze this production data, and determine how to adjust this asphalt mixtures containing local materials. So for this study, you would see like this mixes that what we used for this study was like all the samples that were used were from plant produced acceptance samples taken straight from that asphalt plant. And this mixes, as I mentioned before, were reheated, fabricated for volumetric and BMD without any additional aging. So over here, as I mentioned, like they start collecting from year 2018, and you would see like different mix types: 2S, 3S, 4S, and 2S, 3S, and 4S. So the mix type 2S here would represent 19 millimeter nominal maximum aggregate size. 3S would represent like a 12.5 nominal maximum aggregate size, and 4S would represent like 9.5 nominal maximum aggregate size. And the different PG grades, since Vermont is a cool state, their virgin unmodified binder was a PG 5828, and they went all the way up to like 7028 binders. And based on the different traffic, they had like different gyrations and different samples from different lots as well. So yeah, so for this one, sorry. So for this study, like rutting and moisture, as I mentioned, they were using Hamburg wheel tracking test and they used the Astro T324 to test their asphalt mixtures at 45 degrees Celsius. And they had a criteria of 12.5 deformation, and they used that as a criteria to assess stripping inflection point, and also looking at the rutting potential of the asphalt mixture. And they used the normalized rutting resistance index. For the cracking resistance, they also tested as per Astro T393, and they conducted this test at 25 degrees Celsius to assess the flexibility index of these asphalt mixtures. So all these criteria that they established that you're seeing over here, like a maximum of 10 millimeters. So the other thing that I forgot to mention was like with the 12.5 nominal maximum aggregate, 12.5 millimeter rut depth, they're not finding it to be representative of field performance. So they had used a maximum rut depth criteria of 10 millimeter for Hamburg wheel tracking test after 20,000 passes. and they started running at like 45 degrees Celsius to be representative, and they found it to be successful for their climatic conditions. And for IFIT, they used a proposed criteria of like 10 based on their experience. And also the side-by study was done by North New England Transportation Consortium, done by Rutgers University, and they recommended a minimum CT index of like 150 for New England states, or like the northeastern states. So just to discuss on the results of that, the performance data. So here you see that the overall Hamburg wheel tracking results for the different mix types. And here you would see that for the PG, on the x-axis, you would see the different mix types, like the PG type 4S, which is 9.5, 3S to be like 12.5, and 2S to be a 19 millimeters. And what we did was, with this performance test data, we performed some statistical analysis like the ANOVA testing to see what of this volumetric properties has an impact on this Hamburg wheel tracking test. And what we found was that the PG mix type, the nominal maximum, and air-wise to be a significant factor contributing to this overall Hamburg wheel tracking test results. And we also found from this analysis that significant portions of this PG 5828 for the type 4 has failed to meet that Hamburg wheel tracking test criteria. Though it passed the volumetric, it didn't pass the Hamburg wheel tracking criteria. So we see that the PG 5828 struggles to meet the testing temperature, but did not change significantly. Whereas for a PG 7028, you could see, like, for irrespective of the mix type, you would see that all the PG 7828 mixes had a uniform rut depth of about 4 millimeter. So this emphasizes that by looking onto their volumetrics and the performance data, you could see which of these factors would contribute to the overall Hamburg wheel tracking test results. And this plot over here shows a comparison between the IFIT test and the ideal CT test from the data that were collected since 2020. So you may not have all the data set, but you'd have like limited, like about like 17 mixes. We compared the ideal CT results and the IFIT test results. And what we see is like a very good correlation between these two, ideal CT test and the ideal IFIT test. So this gave us some confidence to VTrans, saying like, hey, yes, like there's a reason why ideal CT could be considered for balanced mix design. So the graph over here shows that for a flexibility index of 10 and a CT index of 150 corresponded well with each other. Like the proposed criteria by Rutgers University of 150 correlated well with what VTrans was seeing with the flexibility index of like 10. So I want to highlight here, like ideal CT and IFIT are completely different tests. Ideally, it should not be compared against each other, because each of these test methods are assessing different properties of the asphalt mixtures. So the comparison here was just to have a general observation between these two tests, not to say one is better than the other, or one is more. It's not a way to replace another test. So here is another graph that shows the cumulative distribution of that IFIT and the ideal CT test results by mix type. So the red line over here shows the proposed, the potential criteria for both this test. So for flexibility index, you would see over here, like the yellow lines is the type 2S mix, and the blue and the green line are type 3, or like the 9.5 and the 12.5 mix, nominal maximum aggregate size. So What you see over here is the 2S or 19 millimeter aggregate mixtures. They about like 50% of the mixes fail to meet the criteria based on our analysis on the data. And a similar trend we could see on the ideal CT test as well. About like 90% of your CT index results for the type 2S are below the preliminary minimum CT threshold of like 150, and less than about like 30% for CT index for the type 4S mixtures. We don't have for that 3S because we don't have the data points for the 9.5 nominal maximum aggregate size. So what we see here is like a good one-on-one correlation between the ideal CT and the iFit test. And here, this graph over here shows the interaction plot between this cracking and the rutting test. The dashed lines that you're seeing are the minimum criteria that the V-Trans was using. So here, like on the x-axis, you would see the Hamburg wheel tracking test rut depth criteria of 10 millimeter and the proposed minimum flexibility index of like 10. And the plot here shows that all the modified mixtures, the PG 7028 mixtures, regardless of their end design or traffic design, tested at 45 degrees Celsius, were in the acceptable region, and they're satisfying that Hamburg wheel tracking test requirements. While the unmodified PG58 that you're seeing on the far right from the project failed to meet the rutting criteria. So of all these 34 projects that we analyzed, 4 projects had a flexibility index somewhere between 9 and 10, while the remaining majority of the 30 projects had an FI value greater than the proposed minimum flexibility index threshold of 10. So here you can say that the modified asphalt mixtures produced are in compliance with the current V-Trans specification and can meet the proposed rutting and cracking criteria. So however, like when you're dealing with this balanced mix design, you need to think about this proposed criteria threshold. So this are subjected to change over the period of time as you evaluate the performance over a long period of time. And the proposed rutting threshold for this unmodified asphalt mixtures can change over the years. So they started off with 10 and they found good success with the proposed criteria. Here is an example, like another similar plot for the CT index as well. Shows similar kind of trend like what we saw for that Illinois flexibility index test, where majority of your mixers with the 150 CT index threshold criteria met, except for like few of the mixes, like 2 of those mixes did not meet the CT index threshold criteria, but were like on the margins. So here are all the comparison of different tests on the overall performance within limits, the PWL specifications and everything. So that's another whole discussion, but I'll just go straight into the findings and the future works of this case studies. So what we conclude from this is that the effect of mixed type on rutting and cracking resistance can be confirmed using the typical mechanical test like the Hamburg wheel tracking test, iFit, and the ideal CT for their Vermont mixers. And what we also found was that effect of design gyration was not found to be statistically insignificant from the Hamburg wheel tracking test results for all the mixtures tested. So V-Trans may further investigate to see whether any further consideration on the gyration level should be worthwhile, or like should they consolidate on the gyration level requirements is even worthwhile considering. And the benchmarking results indicate that the test results appear to reflect the beneficial effects of polymer. So we saw that significant impact on the PG 7028 binders on the rutting resistance. and for final mixtures on the cracking resistance. And what we also found was like a good correlation, as I mentioned, with the ideal CT and the iFit comparison, found that there's a good correlation between these two tests. So if you're looking onto that production aspect, ideal CT is one of those tests that could be considered for BMD implementation on a practical aspect. And based on this correlation, a preliminary minimum CT threshold of 150 is comparable to minimum FI flexibility index threshold of 10 proposed in the VTrans draft specification for acceptance. Results further support further specification changes reflecting both rutting and cracking resistance, which may require minor adjustments to improve the cracking and resistance of the few mixed designs. So all this proposed thresholds that I'm showing here are subjected to change over the years. So it's not like we fix a value and it applies to all the mixes. So based on your mix types and based on the field experience over a period of time, these values are subjected to change, but not significantly, but at least from the baseline, a minimum amount of changes will be observed for this balanced mix design performance test. So this highlights that how performance mix designs can be used to improve your overall performance of your asphalt mixtures. With that, I conclude my presentation, and I'd welcome any questions if you have. Thank you.
Thank you, sir. Now the session is open for discussion.
Yes.
Participants, if any questions, please ask. Sir, there is one question in the chat box. Is ideal CTs appropriate to address TDC in engine payment condition?
Yeah, so ideal CT is similar to our traditional tensile strength testing, except like it evaluates the post-peak slope to evaluate the mixture stiffness. So it is ideal for Indian pavement condition. And in terms of cost aspect, as well as like time aspect as well. And both the contractors and the state DOT agencies can have a minimum investment to evaluate the mixture performance. So it is feasible, and it's an appropriate test to consider for evaluation for BMD implementation. Yes. And most of the states over here in US are also considering ideal CT right now because of its simplicity nature. And you could still use a traditional Marshall press to evaluate the mixture performance. So it is quite easy, and you could still use your traditional Marshall mix design load frames to evaluate the cracking resistance of asphalt mixtures. And you could still use that same Marshall frame press to evaluate the rutting aspect with that ideal RT test, where you have like a cradle J, and you could just crack the specimen and evaluate the rutting potential of that asphalt mixture as well. So you're not investing too much into new technology or training a person extensively. So it's minimum risk factor for the state DOTs and the contractors. So it's completely feasible. Ideal CT is one of the tests that many state agencies are looking into, and it's completely suitable for Indian pavement conditions. Yes. So for rutting, as I mentioned, the ideal RT is one of the tests. So the reason being, you could still use the same Marshall head that you're using for the cracking test. You could still use it for this ideal RT as well. And the cost for those jigs are not expensive either. And the loading rate for both the ideal CT and ideal RT are similar. And the only thing with the ideal RT test or the ideal rutting test is that you have to condition these specimens at elevated temperature. Most of these rutting tests are conducted at elevated temperatures. And this ideal RT, you need to have a conditioning chambers. Even if you're using a Hamburg wheel tracking test, you need to have a way to condition those specimens. But one of the things this ideal RT test fails to address is this rutting potential. And that's where like many of the state agencies over here in US have found that Hamburg wheel tracking test to be more representative of field performance. So about like 50 states, I would say confidently about like 20 to 25 states are confident with using Hamburg wheel tracking test. And they say like it's more representative of field performance in terms of moisture damage and see how their stripping potential is. And some states do also use APA they don't rely on the Hamburg wheel tracking test. They say like APA, the Hamburg wheel tracking test is not a good representation, but APA is more, asphalt pavement analyzer is more representative. So overall, like for, I would say for like Indian pavement condition, Hamburg wheel tracking test and the ideal RT test are more practical than the other tests. So for ideal CT, for example, there are right now in the market 15 different cracking tests. So there are wide options, but you have to see which are the practical tests that can be implemented for acceptance, quality control and acceptance methods. And when you're looking at that practical aspect with minimal cost, minimum amount of training required, that would be like ideal CT and ideal RT, which are more practical and more easily implementable. Because if you're dealing with more processing of that asphalt specimens, it becomes complicated. So yeah, so for rutting, Hamburg wheel tracking, ideal RT, and the asphalt pavement analyzer are the three tests that are currently being considered by majority of the agencies.
So one more question.
Uh-huh.
Sir, is performance-based involvement possible regarding the estimation of mixed production temperatures, mixing and compaction temperature, beyond the conventional EQ or trace angle method? Amarika. Participants, you can unmute yourself, okay?
So mixed production temperatures, yes, you would have an impact. So that's another study that's being, we are still conducting. And since this is in the preliminary adoption phase, like the balanced mix design, we are still trying to see how this mixed performance would say about the production temperatures, how this would impact the overall performance of the mix and stuff. So it's still an ongoing study, and NCAT and Federal Highways are still working on it to address those concerns. And the other also aspect is like when you're dealing with this mix criteria, like there are multiple ways that this performance test results can impact. So we are still working on like seeing which of these tests is applicable for specific needs. So if you're looking at the production temperature, then maybe some tests are more representative, and that is still an ongoing study, and hopefully we would have it in a couple of years.
So thank you for the nice presentation.
Yeah.
And second thing is, Is the balance mixed design concept specifically targeting the use of RAP? That is my first question. And second question is, do we have any criteria to test only for 20,000 repetitions or 50,000 repetitions?
So yeah, so I'm sorry, sir. Like, can you repeat the first question, sir? Like,
Yeah, my thinking is, since that you are using 50% of the RAP
yeah.
in the mixed design, is it because that PMD is targeting exclusively to categorize the RAP and use of RAP in the mixed designs?
Not necessarily, but like over the years, like you would see like the trend has changed significantly. Like the amount of RAP that is currently being used is maximum 20%, and now with the use of like in terms of sustainability, like over here, there's a policy change. Like with the Biden administration, there's a policy change that we have to use sustainable materials. So when you say sustainable materials, there are different ways to make the mix sustainable using low carbon materials, uh, different methodologies. The refining process of that binders that are being used now are completely different. The overall essence is like this balanced mix design is supposed to address whatever changes is going to bring forward in the coming years. Maybe instead of RAP, you would have recycled asphalt shingles or like some other plastics. So plastic is another one that still being evaluated now. So how is plastic being implemented? How is their performance over the years? Like how is it being affected? So in terms of sustainability, this balanced mix design is developed, not specifically for recycled asphalt pavement, but the overall new materials that are being introduced into the market. So there's wide array of mixes that are being added. So the performance of all these mixes vary from very good to very poor, though they satisfy the volumetric needs. So it is challenging, and balanced mix design is one way to evaluate that performance. And your next question, sir, like you had that one? Or?
What in generally when we do the rutting test, we take certain percentage of load from the ITS and we do the rutting test, or even what we call the multiple load application test. When it comes to, in your presentation, you are mentioning a specific number, 20,000 repetitions or 50,000 repetitions. How is it basically varying from?
So that is based on their past experiences. So they evaluate based on, they take the typical mixes, the bread and butter mixes that they typically pave in that state, and they evaluate to see which of these passes would be more representative. So here in Vermont, they use 20,000 passes and say like this is simulating what is actually happening. Whereas in the neighboring state, like down below, like in states like Massachusetts, they have criteria 15,000 passes. So they felt that based on their previous experience with these mixes and this bread and butter mixes, that 15,000 is sufficient to address all the rutting issues and their stripping potential issues. So it's based on their overall past experience over the years and evaluating this specific numbers. So this number is, to start off, it's an initial number. These are subjected to change over a period of time. So like in Maine, they started off with 20,000 passes, and now they're backing it up to 18,000 passes based on the different polymers that they're using now and the RAP that they're using now. They're changing from 20,000 to 18,000, and they changed it not long ago either. So these changes are based on their needs. So we have to select the appropriate mixes and evaluate their overall performance and see how they simulate in the real world conditions. So you evaluate those mixes for you perform mechanical test based on some assumption and then see the overall field performance. And if they correlate well, then use that number. And if not, then you have to tweak around the temperature as well as the number of passes that's being conducted.
Does this have any minimum loading pattern?
Not not that I'm aware of, sir, but like the standard, this to start off, like the Astro T280, the Hamburg wheel tracking standard specifies to start off with 20,000 and go from there. So I'm not aware of that minimum number. Some states I have seen they go as low as 10,000 passes. That's the minimum that I have seen from our past site visit experience. So it can range anywhere from 10,000 to 20,000 passes.
Thank you, sir. Thank you.
Yeah, thank you, sir.
We have one question in the chat
Mm-hmm.
from Shalini. Is there any guidelines to decide on the combination of tests to be conducted based on the variability with respect to climate conditions and material selection in order to arrive at a balanced mix design?
So like this like looking at that examples, like NAPA has a lot of resources, and if you visit the NAPA website, they explain in detail how different state agencies like Vermont DOT has a case example, Virginia has some case examples, Texas and other different states. So if you visit NAPA website, you would see their guidelines on how they would use this test to accommodate their climatic condition and traffic conditions. So NAPA is a great resources where you would find all information and guidelines and how the different state DOT's approach is towards this balanced mixed design implementation. So yeah, there are guidelines, and NAPA, National Asphalt Pavement Association website would give you more information into it.
Hello.
Yeah.
Am I audible, sir?
Yes, sir. Yes, sir.
Sir, this was great presentation.
Thank
I have a couple of questions which I combined and asked together.
you.
The first question involves like already there are many state DOTs have their own specifications for the rutting, cracking, and then moisture
Yes.
damage from the super pave criteria.
Mhm.
And now the balance mix design came up, and then different approaches came up. So
Yes.
can these specification directly adopt for the balance mix design concept, or which is developed way back 15, 20 years ago?
Yes.
And then because the balance mixing approaches came up because of the many new materials came up, additives, polymers, plastic and all. So can we have different specification for the different approach, or can we have the same specification for the all kind of approaches? How the specification is going to change from the super pave to the balance mix design?
So yeah, the specifications would differ from the type of mix that you use. So as I mentioned, like balanced mixer design is not like a one size fits all. So it would change. You could still use your existing one and still develop a BMD criteria for that one using the same volumetric criteria that you have been using. But also, like as more and more mixes come into picture, you may have to revise your specifications to accommodate those new changes. So change is inevitable. So would be the specification where you have to add in some specifications to adapt to the new mixes that are going to be added in that mixes. So back in the days, the refining process was different. Like when I'm talking about asphalt binders, the crude source was completely different. You were getting it from Middle East and from Venezuela Here we would get it from Canada, like other sources. The crude source was completely different back in the days. But now the refining technologies have significantly changed. So the binder that you're getting now are not the same as what you were using back in the 90s. So they have changed the refining process to get more yield out of that crude source. So why I'm saying this one is like your aggregates would differ, your locally available aggregate would differ. Your binder source would change eventually, like the amount of stuff that they're adding into that crude oil refining would change significantly. So this would mean that your specification also would change eventually, and that would also accommodate this balanced mix design. So change is inevitable, and changes into specification would play a role for different mix types and the agency's requirement. So it's up to the agency to decide what they need. Like you can't get a completely balanced mix design. So you have to have like a minimum criteria, like, hey, like I need to have a minimum cracking threshold that I need to satisfy, as well as a minimum rutting threshold that I need to satisfy. If it satisfies these two minimum criteria, then I'm good. And to achieve that one, you have to modify your specifications based on your need, based on the agency's need.
The another question is like in the slide number 29, as where you have presented the performance space diagram between the Hamburg wheel tracker and the iFit.
I can
and
share
where there is the like minimum criteria is 10 and then 12.5 10 you have presented.
Yeah.
And if you can see the same kind of PG 70 and 28 and design 65 mixes, so majority of the mixes lies around the 10.
Yep.
And some of the mixes are way beyond the criteria. So in these kind of conditions, how one can select the whether, because these are the words of the criteria, it's just satisfied. So how can I ensure that will it perform better as compared to there is a way beyond the one, because the same binder and the same mix. So how can we select the particular one?
So here, like the approach here would be like to, in order to, like, as I mentioned here, like you have to put it into the acceptable regions, right? So here what we have to do is like we have to look into the volumetrics aspect now. Like so we saw that this mix is on a broader criteria. So our only option is to maybe put in more asphalt into that mix and see if it's making it more flexible and fall into that acceptable region. So if maybe changing the aggregate source, or maybe considering the effective binder into the picture. So that we have to analyze why that mix had that issues, and then modify the volumetric properties to accommodate that criteria. So if you look over here, like of all the 34 mixes, like those 3 mixes alone failed, but overall, like the majority of the mixes passed. So that means like you have to look more closely into why these 3 mixes have failed, or like are not meeting the criteria. They're not terribly bad, but there's still minor tweaks that can be done to make it more flexible. So this is something that ties up to the volumetric mix design, and it's the agency that have to decide like what are the next steps to improve that mix's performance.
Thank you.
Thank you, sir.
Any other question?
Now, I would like to invite Dr. Gautam Sarang, Junior Scientist, Highway Engineering Division, NATPAC, to deliver the vote of thanks.
Dr. Kingsway, respected participants, Director and Scientist of KSCSTE-NATPAC, distinguished speaker of today's session, Dr. Kumar Veeraragavan. On behalf of NATPAC, I would like to express my heartfelt gratitude to each one of you for making the 17th TransTech Talk successful by your active participation. First and foremost, I would like to thank Dr. Kumar Veeraragavan, Project Engineer, Federal Highway Administration, Mobile Asphalt Technology Center, USA, for sharing his knowledge and experience on the topic, performance-based asphalt mixtures, balanced mix design approach, linking theory to practice. Even though we have heard of the term balanced mix design, many of us were not having a clear idea about it. Dr. Kumar provided an overview on balanced mix design, highlighting its advantages and why we should move from our conventional Marshall mix design and Superfly mix design to this balanced mix design approach. He didn't limit his presentation to the theory of this BMT, but he also explained the case example from Vermont Department of Transportation, USA. On behalf of KSCSTE-NATPAC, I would like to express our sincere gratitude to you, sir, for the time and effort for your wonderful presentation. We are grateful for the knowledge and insights you shared with us today. Thank you, sir. Next, I would like to express my gratitude to all the participants for your presence and active involvement in the session. The questions and discussions that followed the talk showcased your interest in the subject matter, and I appreciate your engagement. More than 85 participants were attending this event online. I thank you all for your time and interest, which made this event a grand success, and we expect your presence in our future events also. We had with us many eminent experts in transportation engineering, including Satish Chandra sir, Veeraragavan sir, Guru Vital sir, Ravi Shankar sir, Gaurav Joshi sir, Sunita madam, Anjaneya sir, and many more. Special thanks to each of you for your presence throughout this talk in your busy schedules also. Finally, I would like to thank our director, Professor Samson Matthew, division heads, and organizing team for the support that made this smooth execution of this program. In conclusion, I believe we all have gained valuable insights from today's technical talk, deepening our understanding on balanced mix design approach for the asphalt mixtures. Thank you once again to everyone involved, and we look forward to hosting more technical talks in this series and continuing this legacy. Thank you all.
Thank you, everyone.
Thank you, sir.
Thank you, sir. Thanks. Thanks, everyone, for your time. And if you have any questions, please feel free to message me, text me, or email me, and I'd be more than happy to help answer your questions. Thank you for your time. And it's an honor to be with all of you. And thank you for your time listening to my presentation. Thanks.
Thank you, sir. Thank you, sir.
Thank you.